Hello everyone, Alex here in beautiful Zurich, Switzerland. Okay, cool, that's working. Today we're gonna shake the foundations of music itself by recreating Ableton or something like that. You ever go to a club and the music just fucking sucks? Well, I decided to do something about it. Um, yeah, so anyways, this is gonna be written in C, so let's see what we got. First things first. Mm, let's just get a file working first and foremost. So I already have a little basic project here. It just has a make file, source, and readme. I copied these over from a different file, so they don't a different project, so it might not even work. But let's just go ahead and hop into source main and then just see what that has. Okay, there's a lot of stuff in here. We don't actually need any of it. Return 0 and that. Cool. And you don't even need this. You might need some of those, but not yet. Okay. Let's go ahead and make main. Right. Yes. Make file. I also copied the make file, so what is all this? Oh, you need some of these, but not all of these. Hmm. Alright, screw this. Step 1, just getting it to fucking run. Which one are we gonna need out of all of these? Oh wait, can we just do this? Can we just that? Anyone actually rely on this guy yet? It's not a green field anymore, is it? Oh, God. Maybe. What? There. Rand is fine. We can copy it. Source rand. Let's see. I'm not gonna use it just yet, but of course. Okay. All right. Cool. So we are building at this point. Let me just do this real quick. This is a Vim artifact. Also, debug artifact. Should be called tilt yard. Out. We'll call it Blue Rhapsody. That was pretty good. Let's make the make file actually. Oh, click. Tilt yard. No more tilt yard. Only Blue Rhapsody. Make main. Get status. RM tilt yard. Get status. Get add. Basic build of make main. All right. Cool. Let's see if we can just get it to write anything to a file, because that's going to be I've never done that before, I think, so it should be fun. Gotta do this. I'm gonna have to phone a friend for this one. Bye-bye. C, write file, how? Here we go. Whoa. No, we need write bytes to a file. C. We need raw bytes, I think. Let's see some human answers from the old. That's it? Wait. What the hell? Oops. What's going on? Write n bytes to a file. There we go. Okay. Pointer to the array of elements to be written, converted to a const void. All right, let's just do this. Pointer, let's do. Is this legal? No, let's do it. Let's do some actual data. What is U8? I'll tell you. That's U8. Just U8 type. Include that. Alright. U8 star, I don't know, data. Data is equal to malloc 8 times size of U8. Data 0, data 8 is equal to 0. I don't know, 7. And then we can do free data. Very simple. We're basically going to write some garbage, null terminated garbage to a string, to a file, and see how that works. Need a napkin. What the fuck are they? Am I blind? I don't know. What's like ASCII? There we go. Let's just do A. Decimal 97 sounds good. 0. Super simple. Okay. Write hello world to it. Okay, so we just need to do data. So that one's taken care of. Maybe keep it explicit. What is it? Const void star. If you want a const void star, I'll give you a const void star. Here you go. Data. You want size type, right? That's just going to be size of U8, and we'll do 8. We'll get back to that later. File stream is going to be more interesting. We actually need to set this up properly. What do we do here? What do we need to do? There we go. Copy the documentation. Can't go wrong. File. Wave. File. Whatever. Whoa. File name. Not read, no. We need write. Fopen. Now we can do close. Oh wait, this is probably a good idea. Fopen close. P error. What the fuck is P error? I've never seen that before. We just do return 1. Easy. Now we're just gonna do a single one right here. I'm not gonna do puts. We're just gonna do fright. File, maybe. Close. Oh wait, if we return, we don't need to do all that. We can just proceed. There we go. There we go. Maybe this will work. Let's find out. Make main. Ooh, no. What is null? Where did that come from? 0. Or just not file. Oh, we don't need read. We need what do we need? Isn't it WB? It's WB, right? So WB. Yeah. Right binary. Okay. Let's try that. Go. Oh. Oh. That's weird. Oh, because it's a file, not a string. Okay, well, cool. We can write files now. That's basically the general idea. Try to wave file. Git add source main, git commit. We can now write binary. Possibilities are endless. Right. Oh, we don't even have a remote repo. Don't need one. Not yet. Okay, where was I? Let's all right, we've written a file. Now we need a actual wave file. So let's see what these look like. What the hell? Okay, waveform audio file. Waveform. We need a format chunk. We need wave data. I think the Wikipedia page is a bit better at this. Wave Wikipedia. Wave file. Here we are. Oh, same exact thing. Okay. Riff wave. Okay, this one is the tricky one. What is a What does this mean? Might be good to define a struct for it. Later. And they literally tell us what it looks like. Let me see if I can find it. Let me find the riff. We just need like this part. This part is defined in the riff documentation, which is right. Here we go. Let's see. The chunk ID. So the chunk ID is riff here. Oh wait. Riff chunk with a form type of QRST, and then the data portion. Okay, so this is a riff chunk with a form type of wave. All right, so what does this actually look like? Chunk ID identifier. Huh. Chunk ID identifier. Is that it? But how do you know how many chunks there are? Start from the top again. I mean, it makes sense, but let me see the riff format here. I don't. Hmm. Hmm. I mean, hmm. I mean, I don't know. Let's just try this. Mm, like that. That's legal, right? Tag. I mean, what do you even waveform? Tag. Format chunk. Wave data. Wait, but there's no way of knowing how big that's going to be. Right. Hmm. Hmm. Data. Is this possible? What would we call it? Byte data? Wave data? Maybe. Let's also do format type def struct format chunk. This is going to be 44 bytes. See if we can get it right. What do we need? Format chunk. We need word. What is word? Wait, is this the same thing? What? Wait a minute. Wait, this isn't the same thing. What am I looking at? What? Where did this come from? Oh, wait a minute. This just told me exactly what I needed right here, didn't it? Hold on a second. Hold on a second. Oh, this is just too easy. Watch this. Now we just type def these things. Type def struct riff chunk 4 bytes U32 and a U32 file type block name. We could just take these names. Why not? U32 file type U32 easy money, just like that. Thanks, Wikipedia. Oops. Overall file size minus 8 bytes. Yeah, good luck with that. 4 bytes riff. Cool. Chunk describing type def struct format chunk. We'll just all these. Thank you very much. All right. 4 bytes is going to be a U32 format block ID. All right, we're telling us which block we're using, which is the basic gist of riff. All right, cool. Format block ID, block size, format chunk. Audio format. What? Wait. Where does this come from? Audio format. Alright. U16. I don't know why you need 2 bytes for that. I feel like you only need 1. Number of channels. Also a U16. Frequency. Okay, this one's more interesting. Bytes per second. Wait. What? What? What do you mean number of bits per sample? What is this supposed to be? Wait. get it. Chunk containing data chunk. Sample data. I measure this as a U18, a U8. Or it's like that, I think. Obviously, sample data is just whatever you want it to be. And then we also have a U32 and another U32. Cool. Data chunk, of course. Let's see if we can use this. First and foremost, I think they have some examples. I see. Okay. So we're looking at 48 hertz, 16-bit mono. Okay. 16-bit. Well, this is interesting. I think we should try to make some of these first, so let's do this. Riff. I don't even know. U8 star wave is equal to malloc something. And we'll do riff chunk star RF. Riff chunk is equal to wave. And we'll just do wave, say RF, file type block ID is equal to X52. I wonder if I can just do this. 49, 46, and 46. Cool. I think we'll have to come back to this one later. File format ID. Oops. We want 57, 41, 56, 45. Okay. Then we skip ahead to format chunk FC is equal to format chunk make this a void star so we can do some quick math on it. Wave plus size of riff chunk. This is a constant at compile time. It's not a problem to do. We gotta fill out all of these. This is like the more interesting one where we actually set parameters. There we go. So we'll do. There we go. All right, these are already documented up there, so we don't need them again. Format block ID. Right. 6D, 74, and 20. Okay. Block size, chunk size minus 8 bytes. Which is 16 bytes here. Oh, of this chunk. Is that right? Where are we getting 44 bytes from? 12, 20, 24, 28, 30, 40. Oh yeah, it is 44. All right. 16 bytes here. Maybe that'll work. Little Indian. What does that mean? We're gonna find out. I don't know. What is TCM? I guess we'll do one. One channel, mono. So 1, 1. Frequency, sample rate in hertz. So this was requested as 4800 or 48K bytes per second. Okay. Now, if I remember correctly, if we do it like this, size of data chunk will just be these two, and then sample data will kind of be like thrown out because we don't know how much it is at compile time. So I think this is going to be, if data chunk is just going to be size of it is going to be 8. chunk star DC is equal to data chunk star wave plus size of riff chunk plus size of format chunk. Okay, and we just do DC data block ID is equal to 0x64 61 74 and 61 data. All right, and then we can do DC data size is equal to, come back to that one, and then yeah, U8 star data sampled data is equal to DC sampled data, or this. Or we can do this. Yeah, good enough. And then we can just start writing like sampled data. I don't know, 47 is equal to a million. I don't know. And the thing to remember is that it is like the endianness of it isn't obvious. So low order byte, high order byte, which I'm pretty sure is opposite from how it's usually done, but we'll come back to that in a second. We first need to do some calculations for some of the data types. Let's see. We're actually gonna start from here and kind of work our way backwards. Let's do this. Static const. What is frequency? U32. U32 frequency is equal to 4800. 1000. We'll do that here. Call it sample bit. So U16, do 16. Okay. Any interesting number, I'm just gonna pull out basically, because we're gonna need it for some calculations. Block size 16, audio format, number of channels. Oh, mono versus stereo. Yeah, this is interesting, huh? Okay. Just you wait until we start getting into stereo. That's for later, though. For now, this should be enough. All right. What is the data size? Let me add a new thing. Okay, so duration will help us determine exactly what we want to do. What it's going to look like is Uh, you said data size in bytes. I assume this is how many bytes it is. Sample size. What the hell? What does this mean? Weird. Sampled size. Is this in bytes? I'm gonna assume it's bytes. All right. Data size is gonna be frequency. It's not frequency, is it? Yeah, it is. Sample bits times duration. So, multiply, then divide. Okay. So this is gonna work out to 96,000. Okay, so that's data size. Now we can go back and fill some other things in, like file size. File size is this thing. Almost. No, that's actually not it. Overall file size minus 8 bytes, so these two are not included. Minus 8 bytes. Is that right? So file size is like this. This is the file. Which is confusing because we also have an actual file size. Okay, so just make that clear that we're just doing file format ID. Okay. Plus, we need to pull this out. data bytes equal to frequency. I forgot I basically disabled caps lock. Duration times sample bits. Okay, and then we just do that, and then okay. Okay, and then last but not least, maybe we should move some of these up. Size of riff chunk plus size of format chunk plus size of data chunk plus data bytes. Yeah, that looks pretty good. Actually, we can call it something like this. Real file, real file size is equal to this thing. Okay. And then oops. Okay. Alright, well this is going to contain junk data, so it's not going to be initialized to 0, so I'm kind of curious to see what even happens. Okay, let's just see if we can write this thing. What do we want to call this? 1A dot wave. And what we're going to do is wave, which is already a void star. Oh, but it's not a const void star, so if you wait, real file size and the file. This could work. We don't need this anymore. Oh, we do need to free the wave though. And let's see what happens. Fingers crossed. Nice. 17 errors. Cool. RF is not defined. Oh, that's an easy one. It's called RF. Boom. Okay, only 16 errors. And it's all about, like, these. Let me just fix that warning real quick. That's an easy one. Good. That one's gone. Cool. Yeah, we could definitely fix all of those. All right. This is a U32. We can just do. Times wait. Actually, no, I think it's the other way. Right? Little Indian, big Indian. I have no idea. Let's see if this works. This might not even work because oops. This thing might just push the values completely over the edge, and they just might get turned into 0. This is how we used to do it before LLMs, by the way, back in the old days, like 2 years ago. 52, 49, 46, and 46. All right, maybe that works. My bad. Oh. Well, I'm sure it works, but Little Indian. I forget what this means. Least significant byte at the lowest memory address. Wait a minute. Oh. Well, there's our WAV file, by the way. I mean, does that look right to you? Well, actually, it does look like it's uninitialized. That's good. Well, you can see format, data, they're all backwards. So that's good. Glad I got that right. Okay. This is gonna bite me later, but let's just do this. 46, 46. Wait, I mean, maybe it works. Let's just find out. Yeah, 1A.wave. Let's hear it. Let's hear it. Well, duration is 0, which is not a good sign. Maybe let's try this. Well, duration is still 0, so that's not a good sign. Oh, there we go. Perfect. Okay, well, let's try flipping the order then. 46, 49, and 52. Let's see what we get. BI1A dot wave. Okay, now we have a riff, but then there's something weird going on there. What the fuck is that? It's so weird. What happens if we open it with QuickTime Player? What if we open it with VLC? Damn it. Okay. What if I do this? Okay, so that's all we have to do. We just need to swap these and we're good to go. Exciting, huh? 56, 41, 57, 20, 74, 60, 66, 64. Watch this. It's a thing of beauty. Listen. Can you hear it? 10 seconds of pure, unfiltered silence. Hello, darkness, my old friend. It's fun to come to talk with you again. Oops. Actually, we'll add the, let me change that back to 1 second and save what we have because this is huge. This is actually huge. You can get rid of our file. Status git add dot git ignore git add source git commit created the first wave file, and I'm just gonna move it into golden. So we'll do. Okay, wait. Oh. We just don't want to save all of them. Okay. All right, cool. Let's actually do something about it. Endianness, what the spec says, etc., etc. All right. 1B, a tone. Replace the sounds with a 440 hertz sine. Listen, clean, steady A4. Then parameterize frequency, duration, amplitude, and sample rate. Gladly. Well, we already kind of parameterized it, didn't we? Okay, 440 hertz sine. Let's see if we can wire that in. Yeah, we can do really fun stuff now. 16 note frequency is equal to 440 hertz. Oh, it hurts. Now how do we actually want to think about this? Frequency means that it does 440 full, I want to say rotations, but yeah, rotations through circle in 1 second. Thus, y is equal to if it was 1, it would be 2 pi x. But if it was 440 times, it would be 440 times 2 pi times x. And x can be this should be sample frequency, not just frequency. Here. Okay. Okay. You'll see what I'm doing. Okay. 4. U32. I is equal to 0. I is less than num samples. I plus plus. Okay. We need to figure out where we are exactly into the data. And we're gonna need to do like some weird little Indian stuff, but let me just give you the amplitude. So U16 amplitude is equal to sine note frequency times 2 times pi times I divided by sample frequency. Multiply first, then divide. I mean, This is an easy equation to write out, but how do you actually implement it? I don't know. Also, it should probably be higher than just between 1 and 0, so it should be some kind of scaling here as well. I'm not really sure what though. Let's just call it amplitude. 16 amplitude. Yeah, is equal to, I don't know, 1. No idea. Sample amplitude. And do amplitude times that. Okay, cool. That looks pretty good to me, except for, sign isn't defined. So now we have sample amplitude, and what we need to do is sampled data something is equal to something. Oh, and the other one is going to be horizontal. They call it max U8. I'm sure it's fine. It's going to be these are bytes. So 2 times I and 2 times I. One of these is +1. I don't know which one though. Lower order byte, higher order byte. I think the first one is the and, so I think it's this. Like that. I think that's about right. Okay, I think that's all we need. And let's make this 1B. See what happens. Nice. Oh yeah. Sample frequency. Frequency. Cool. Okay, 2 warnings and 2 errors. Cool. All right, we got sign. Isn't there like sign 2 or something? Standard library. What if I don't want to use standard library? Oh, you probably do the Euler's formula, right? Euler's or Taylor series. Pi. That's it. Just pi. Oh, it's a double. Is that gonna be a problem? Oh, fuck. Something should be a double here, shouldn't it? Let's see what happens. Pi. Cool. Oh. We got something. Let's see what happens. Watch, my ears are about to be blessed with this beautiful sound. What? Seriously? Um, um, let me test something real quick. D, I guess. Note frequency times 2 times pi. Uh, what the? What is this thing? Oh, so this is a float. Gotcha. So this is a float. Do we want to deal with floats? I maybe. Sure. Oh. Wait, but wait, go back. PCM integer. What is a PCM integer? What does it mean? What's a signed integer? Oh. What the? Okay. All right. It's signed, which doesn't help, but you know. Okay, amplitude. Let's turn this up a bit. 10. Okay. That seems more right. Let's hear it. I don't hear anything. What the fuck? Let's turn it up a bit. Wait, is this even gonna work? Wait, how? How could it be unsigned but then placed so weirdly? Oh yeah, that helps. Well, you can see the sine waves actually. That's pretty cool. All right, let's try again. Did you hear that? Let's go. Let's go. Let's go. We got our first note. We got sound. Nice. What can I say? That was easy. All right. And then parameterize frequency, duration, amplitude, and sample rate. Let's start with frequency. Let's try A3. Oops. Should be one octave lower. Oh no, do not open iTunes. Nope, nope. Nice. Let's try one octave higher. Yeah. Okay. Frequency is parameterized. Duration, easy. 10 seconds of beautiful goodness. No, the other one. So beautiful. Okay, duration's good. Amplitude we just did. Sample rate. This one's a bit more interesting for me. I wanna hear how it goes. I mean, it can only be like 8 or 16, right? Like what else could it be? Wait, yeah, it's at the bottom here. Here we are. 16-bit, 16-bit, 8-bit, 4-bit. How does that even work? Just sounds like shit, I guess. Alright, let's do 8-bit. Then we do this. Otherwise, we do this. pretty simple. It's just same thing except this is an I8, and we don't multiply, we just do that. Let's see what that sounds like. Oh, we don't need a printf. Oh, there we go. Let's see what that sounds like. If it even works. Why wouldn't it work? Can you hear a difference? Jesus, scared the shit out of me. Is that really what 8-bit sound sounds like? Wait, that's not even the same frequency. Hold on. Let me mess something up. Yeah, it only played till 5 seconds. Oh. Wait, no. Someone's hard coding 16. Number of samples shouldn't have changed. Let's see. It's not that. It's not that either. Is it even the same like frequency though? Did I miss something? Wait, didn't log anything. Oh. What the fuck is this? Oh, oops. These are way off. Why is it so different? What is going on? Oh. Wait, oh. I'm sorry, what? This is gonna sound interesting. Oh, there it is. Hmm. First of all, what the fuck is going on here? I guess plus 128. See, this actually looks more like a proper wave. This seems to be completely different in the way that it see, it goes up and down way faster, and I don't understand why. Hmm. What the hell? Oh. Hmm. Oh. We need like a separate amplitude. Maybe amplitude should be like. I have no idea. Um. Okay, fuck it, we're doing this. This will now represent like max, like what percentage of the max. I believe here for 32, for 16 it can be up to, so we're only doing about 1/40th, or 1/40th, so there. Let me just wire that in. There. I think that should work. Maybe. Max is going to be 30. I want to say 15. Pray for my speakers. Alright, here's a beautiful 16-bit. Okay, and a 8-bit. Huh. This might be barely audible. Oh, that is so weird. Alright, let's hear it. It's got a nice little ring to it, doesn't it? Okay, well. Oh, that's pretty good. Cool. Alright, so that one's pretty done. Equal temperament derived, then a scale. Before generating the scale, derive the tuning system yourself. An octave, double frequency, and 12 equal notes. What must be the ratio between each adjacent semitones beats? 3-line derivation, you'll never need to look up a note frequency table again. Then generate a 25-note chromatic scale from A3 to A5, each note 200 milliseconds. Brief silences in between in one wave. Challenge accepted. Okay. Equal 12-note temperament. Okay. From here we can derive everything else. Static const U16 A3, you said? Yeah, equal to A4 times 2. 5 put it this way. A3 is equal to, or A3 times 2 is equal to A4. However, you also have the 12 note scales, which is A. Oh god, am I gonna mess this up? Let me visualize a piano. Uh-oh. That's not helping. I'm just gonna write out what I know. There we go. That's our, these are our guys. Now, there's some value, let's call it E, such that A sharp 3 is equal to E times A3. And then you have B3 is equal to E, or let me make this clear, A has 3 times E. And so on and so forth, all the way until A4 is equal to G sharp 3 times E. Now what is this value? Okay. I got cut while swimming today. That's not ideal. Let me put it this way. No, this isn't quite it. It's right? So therefore right? I guess, my guy. I guess so. What do we even want to call this? Static const semitone x mult is equal to, how do you even, I only need to do this once. Oh. Wait. Double. Okay, easy. Um, 2.0, 1.0 divided by 12.0. Go ahead and print this guy out. Public static const. Be return double. Uh, F. Okay, let me make that clear then. It's just good to think about how many bytes things take up. Okay, yeah, cool. And now we're gonna do long float, semitone molt. Let's see it. What do you mean? Yes, it is. What are you talking about? Oh. Okay. Amazing. We printed out LF. 1.059. Does that make sense? Close enough. Okay, so what can we do now? This is gonna be the dumbest way to do it, but fuck it. This is gonna lose precision each time. Oh god. This is so dumb. I just want to know if it works though. Okay, oh god damn it. We can just do it like this. This should be a float. Yeah. I think that should work. Okay. See what happens. Nice. 139 restoration. Yes. Go. Nice. Oh no, bus error. It's not good. Where? Hmm. What the hell? Why does it get so high? Hmm. It's like random. Why? Wait, it shouldn't even be going that much. 2600. Yeah, that's about right. So why does it keep going then? Oh. Oops. Silly me. Cool. Still a bus error. Why? Oh. I know why. How much do we need? 20 seconds. Just messing around, really. Psych fault. Nice. Why? What? Immediately? Okay, it's at the same spot. God damn it. Oops. Okay. Fingers crossed. Wow. Very cool. Alright, I think that's enough for one day. We'll call this M01 scale. Nice. Let's see how high we can get. Mm. 48. Those are all very much in range. Should get to bed. One octave higher, please. Cool. A little hearing test there. Let's try it real low. Maybe like 880, 440, 220, 110, 55, 20, 27.5. Right? Yeah, because 55. Right. Yeah. It's gonna start really low. There. Cool. Alright, I think that's enough for one day.